chemical bonding to the covalent bond. So the last one we talked about this complete transfer of electrons in the ionic bonding. Now we're going to talk about a completely separate type of bonding where we don't get complete transfer. And that's this covalent bonding, where we are sharing electrons. Typically this is between non-metal. We're going to share electrons so that we get to this sort of octet guiding principle. So we want to have that filled outer level. But in this case, instead of transferring electrons, we are going to share them. And you can see in this graphic here that as we bring those two atoms closer together, we get a point where there is an interaction between, we're balancing the attraction between the nuclei, or the electrons, and the nuclei, and the repulsion of those like particles. So there's this sort of balance achieved when we share those, where there's attraction between both sets of the electron in both sets of nuclei. It's overwhelming the repulsion of those, the electrons to each other and the nuclei themselves. So there's this benefit of being sharing these electrons. So then we can have sort of two different kinds of electrons within these molecules or atoms. Right? We can have the ones that are being shared between two nuclei, and then the other ones that are only related to one. So the shared pair is what we refer to as the bonding pair. Right? And we can, when we draw these out, we can either use those as two dots in between the two nuclei, or we can represent that sharing by a line, where each end of the line represents a dot, or the line, two pairs of electrons. Right? And then those outer ones we're calling lone pair. They're electrons that aren't shared, but they're lone pair to that atom. Right? So we have these two different types. Excuse me. We can then talk about what we call the bond order, is the number of shared pairs of electrons that we're sharing. So if we're sharing a single pair of electrons, that would be a single bond, which would have a bond order of 1. If we're sharing two sets of electrons, or a total of 4 electrons are being shared, then that is a double bond and has a bond order of 2, and so on. 3 pairs of electrons being shared, or a total of 6 electrons, that is a triple bond and has a bond order of 3. Right? And then we can relate how strong this bond is by the bond energy. Right? So the stronger the bond energy, or the higher the bond energy, the stronger that bond. Right? And again, this is going to be a function of both the order, the number of bonds in pairs there are, but also the bond length, right? The distance between those. So the further out they go, typically those are going to be lower bond energies. So in general, we can say the higher the bond order, the shorter the bond, so we're bringing those two closer together to share more electrons, which is going to give us a higher bond energy. Right? So the longer the bond, the lower the energy. So for any given two sets of atoms, the shorter the bond, the stronger that bond is. So we can look at oxygen and oxygen. If we have a single bond, that's going to have a smaller bond energy than if there's a double bond there, which would be shorter in case if we had a triple bond. And in general, this bond length is going to increase down the periodic table, as you would expect. Those molecules themselves get bigger, so the ability for those nuclei to come close together is also going to be reduced. So the bond length increases down as the molecules get bigger, and decreases across the period. Right? Again, it's a function of that atomic size, essentially. So the bigger the atom is, the further apart they're going to end up being. Right? So, like we said, this is opposite then. The further apart they are, the weaker the bond. So if we increase the bond length, the bond energy is going to go down. Right? And we have a table in your book, and here it is, here showing all of those bond energies. And we can look, for example, at the bottom here. If you look at it closely, you can see, if we look at carbon and carbon, on the top here we have its bond energy, average bond energy for a carbon-carbon with a bond order of 1, a single bond there, is 347. Right? And it has a length of 154 picometers. If we look at the double bond down here at the bottom, then we have a energy of 614, again higher in energy, and the distance has gotten smaller. We're at 134 picometers. If we go further over, down to the bottom here, the carbon-carbon triple bond, now our bond energy is higher still. Increase the bond order, increase the energy. Here it's 839, but as that bond order increases, the length is going to decrease. With the triple bond, it's 121 picometers. Right? So then if we know the types of bonds, we can use these bond energies to sort of relate that to enthalpies of reactions. Right? So we can take these bond energies and calculate enthalpies of reactions. What we're assuming is we're going to take all those atoms that are bonded together and break them all apart into individual atoms. Right? And then we're going to reform bonds in the products. So the reactants we're breaking up into the atoms, and then in the products we are reforming completely new. So we can calculate the enthalpy of this reaction as being the sum of the bonds broken, because we have to add energy in to break bonds, and then we should get energy out when we form them. So the enthalpy of change for this one is going to be the sum of the bonds broken plus the sum of the bonds formed. Right? So the difference there is this delta H of reaction. So we're going to look at all the bonds present, essentially break them all in the reactants, and then look at all the bonds present in the products and form all of those. The sum of those two things is going to be our delta H of reaction. So we're talking about sharing, and we know that most things, and atoms included, don't share things evenly, right? So we have this property called electronegativity. It's the ability of an atom within a covalent bond to attract those electrons towards it. That's the electronegativity. So the ability to pull those electrons that it's sharing towards itself. If they're completely shared, there's no difference in electronegativity, they're sharing equally, that's what we call a pure covalent bond. If there is this unequal sharing where one is drawing them closer to it, that was we call a polar covalent bond. Right? So the one that's drawing electrons to it is going to have as more electrons, which are negatively charged, we'd have a partial negative charge. The one that's losing those electrons, or the electrons are moving away from, is going to be partially positive because it's losing some of that negative electron. We call that a partial positive. Right? And this is all based on this electronegativity. And here's a figure of all the electronegativities across the periodic table. We see in general a similar trend to what we've seen before. So in general, the most electronegative species is fluorine. Right? So at a peak of its electronegativity value there was 4. Generally, electronegativity decreases as we go down, as the atomic size increases, right? And increases as we go across the periodic table. So it increases up and towards fluorine, right? Just like most of the other periodic trends that we saw. Right? In general, because everything is increasing that side, nonmetals are more electronegative than metals. If we're measuring these electronegativities, what we can have is a sort of a spectrum. Right? If we have a large difference in electronegativities, then that unequal sharing is so much so that one atom is actually going to physically take those electrons away. Right? In that case, we call that an ionic bond. We talked about that the last time. Right? If it's just sort of pulling them a little bit, that would be what we call a polar covalent. If they're sharing fairly equally, we call that a pure covalent. So it's really this sort of spectrum of values. And we can calculate that using this differences in electronegativity you can see behind me. Right? If we have a large difference, which we signify as a difference of electronegativity about 1.7, anything greater than that, we call that an ionic bond. Between 1.7 and 0.4, this difference in electronegativity, that is what we call a polar covalent. Anything that has a difference less than 0.4, we could call that a mostly covalent or a covalent bond. So these absolute values, or these magnitudes, are sort of nice to have, but really we're looking at differences in location on a periodic table. If they're fairly close together, we would say that's going to be a covalent compound. If they're further apart, like so fluorine and sodium far apart, that's ionic. Right? If they're somewhat of a distance apart, then we call that polar covalent. Right? It's sort of a full spectrum. We can make estimates based on their periodic location. Right? The way we depict these is we're showing the movement of the electrons. So we're always showing movement towards the more electronegative. So if we look at hydrogen fluoride here, fluorine being more electronegative is going to pull that shared pair towards it. So the electrons are moving towards the fluorine, as you can see in this arrow, which is leaving the hydrogen side without electrons or partially positive. So we can depict this polar bond in that way, where half of the bond is more negative, the other half is more positive. We can also use this sigma for a small change where we have a partial positive charge on the hydrogen versus a partial negative charge on the fluorine. Remember, in this case, we're sharing electrons, so we don't have that full plus or minus. It's only a partial. It's some fraction of a full charge. So we're going to look at these calculating enthalpies of reactions using the bond energies. We're going to do some initial sharing, and then depict these polar bonds. The next lecture we'll be talking about actually drawing molecules and then using all this we've learned and putting it together to do some more complicated Lewis structures.